Okay, so here's part 2 of the electricity and magnetism practice final exam. So number 13, long solenoid has N turns, length L, and radius here A, and carries current I. Assume L is much larger than A. A, B, C, D, E. What we could say here, find the magnetic field inside the solenoid, find the magnetic energy stored, derive the inductance. If the current increases as I of t equals alpha t, find the induced EMF, and explain the sign of the induced EMF using Lenz's law. Okay, so inductance problem, magnetic field B equals mu naught N over L I, volume pi A squared L. Our energy density is going to be here equal to the B squared over the 2 mu naught. And now our energy formulas are given here. Okay, this is canonical for the most part. Here are U, and here's our inductance, L sub I and D. And if I of t equals alpha t, then we get the following. We're going to get for our negative L sub I and D, di dt equals negative L I and D alpha. And the negative sign, it should be noted, signifies the induced EMF opposes the increase in current. Okay, so that's more of a canonical type problem. A lot of these are. Okay, but number 14, this is pretty much standard topics for electricity and magnetism. Okay. 14, a parallel plate capacitor with circular plates of radius A and is charging with current I of t, A, B, C, D, E, respectively. Find the electric field between the plates as a function of charge Q of t. Find the displacement between current density. Show that the displacement current between the plates equals the conduction current in the wires. Use the Ampere-Maxwell law to find B of R between the plates for R is less than A, and find B of R for R is greater than A. So it's displacement current and Maxwell correction problem. So electric field between the plates is here. E equals Q of t over epsilon naught pi A squared. Our displacement current densities are here for J of D, J of D, J of D. All right. And here for our R is less than A, our B of 2 pi R equals this. So I sub E and C is I of I times R squared over A squared. So B of R equals the following here. So B of R is greater than A, mu naught I over 2 pi R. And our total displacement current I sub D equals J sub D pi A squared equals I of t. Okay, so that's pretty much all. I went a little bit out of order, my apologies, but that's all for 14. Moving along to number 15. So number 15 here, plane electromagnetic wave in vacuum has electric field E of z comma t equals E naught cosine of kz minus omega t times x hat. Find the corresponding magnetic field. Use Maxwell's equations to show that omega equals ck. Find the Poynting vector. Find the time average intensity. Find the radiation pressure if the wave is normally incident on a perfectly absorbing surface. Okay, so electromagnetic waves. So E equals E naught cosine of that quantity kz minus omega t, close parentheses, x hat. The magnetic field points in y hat. B equals E naught over C cosine of that kz minus omega t, close parentheses, y hat. So Maxwell's equations require omega equals ck. So our Poynting vector is going to be equal to that 1 over mu naught crossed times E crossed B. So our Poynting vector is this E naught squared over mu naught C cosine squared times cosine squared of, kz minus omega t z hat. Our average intensity is or E naught squared over 2 mu naught C equals 1/2 epsilon naught C E naught squared. And our radiation pressure on the observing surface P sub RAD equals that average intensity divided by C, so 1/2 epsilon naught E naught squared. So that's number 15. Moving along to 16. Okay, 16. Plane wave traveling in the plus Z hat direction strikes a perfect conductor at Z equals 0. The electric field is polarized in the X hat direction. A, B, C, D, E. Write the incident electric and magnetic fields. Write the reflected electric and magnetic fields. Enforce the boundary condition at the conductor surface. Find the total fields for Z is less than 0. Identify the nodes and antinodes of the standing wave. So this is a reflection from a perfect conductor problem. So our incident wave is going to be E sub naught cosine kz plus omega t x hat, and for electricity, and for the magnetism, E naught over c cosine of kz minus omega t y hat. Okay, reflected wave travels in negative z. To make the tangential electric field 0 at z equals 0, our E sub r equals negative E naught cosine kz plus omega t x hat. B sub r equals positive plus E naught over c cosine of kz plus omega t y hat. Our total electric field equals E naught times this quantity, cosine of kz minus omega t minus cosine of kz plus omega t, close bracket x hat. And using identities, E would equal 2 E naught sine kz sine of omega t x hat. Total magnetic field is going to be equal to E naught bracket cosine of kz minus omega t plus cosine kz plus kz minus, sorry, right here, kz minus omega t plus cosine kz plus omega t, close bracket y hat. So magnetic field is going to be 2 E naught over c cosine kz cosine omega t y hat. Okay, when employing identities. And from here, let's see, electric nodes, sine kz equals 0. Our z is going to equal to n lambda over 2. And our electric antinodes, z equals the quantity 2n plus 1 lambda over 4. Okay, moving along to 17. Whoops. Sorry about that. 17. Starting from Maxwell's equations in vacuum with sources, dot product of del and E, given here, dot product here of del dot B equals 0, cross product here of del and E equals this partial, negative dB dt. These should look familiar, starting from the Maxwell's equations in the vacuum. These should look familiar. We're going to derive the electromagnetic energy conservation law, this partial of U with respect to T, plus this del dot S equals negative J dot E. Identify U and S. Okay. All right, so conservation laws. So here's what we're going to do. We're going to start with E dot dotted with the cross product of del and B minus B dot the cross product of del and E. Use the identity, so this requires a lot of the identity stuff. So del dotted with E cross B, that's going to equal B dot del cross E, minus E dotted with the cross product of del and B. Okay, so from here, now from Maxwell's equations, that del cross B, that equals that mu naught J plus mu naught epsilon naught, partial of E with respect to T, and then we have del crossed with E, that's negative partial B with respect to T. So substituting and rearranging this dt partial times the quantity 1/2 epsilon naught E squared plus B squared over 2 mu naught, close parentheses, plus del dotted with 1 over mu naught E crossed with B. That's going to equal negative J dotted with E. Okay. So from here, U equals 1/2 epsilon naught E squared plus B squared over 2 mu naught. And S is going to equal 1 over mu naught E crossed with B. And again, I'm going through this at a quick speed, so you have this as a reference for you to try it and just check your work. Okay, and then number 18. Okay, number 18, we have a long coaxial cable, has inner conductor radius A, outer conductor inner radius B, and vacuum between them. The inner conductor carries current plus I, and the outer conductor carries current negative I. The inner conductor has charge per length plus lambda, and outer conductor has charge per length negative lambda. So A, B, C, D, and E. Find D of R for A is less than R is less than B. Find B of R for A is less than R is less than B. Find the Poynting vector S. Show that the electromagnetic power flow through the annular region equals VI, where V is the potential difference between conductors. Explain physically how energy is transported from source to load in the circuit. Okay, so synthesis problem, coaxial. So part A, for A is less than R is less than B, Gauss's law is going to give E of 2 pi RL equals lambda L over epsilon naught. So our E equals lambda over 2 pi epsilon naught R hat. For letter B, Ampere's law, B of 2 pi R equals mu naught I. So our B equals mu naught I over 2 pi R phi hat. Letter C, the Poynting vector, S is 1 over mu naught E cross with B. And since R hat crosses with phi hat, that equals Z hat. S equals that lambda I over 4 pi squared epsilon naught R squared Z hat. And for letter D, power flow through an annular cross section. So set up this integral. P equals integrated from A to B of S dA, where dA equals 2 pi R dR. So P equals from A to B, integrating this lambda I over 4 pi squared epsilon naught R squared 2 pi R dr. So P is lambda I over 2 pi epsilon naught, integrating A to B, dr over R. So integrating that, that's natural log of R, ln R. Technically ln absolute value of R, but so P equals lambda I over 2 pi epsilon naught ln B over A. The potential difference is V equals this integral from A to B, E dr, and V equals lambda over 2 pi, that epsilon naught ln B over A. So then P, that comes out to, that's V times I. And for letter E, energy is transported through the electromagnetic fields in the space between conductors, not merely inside the metal wires. Okay, so I went through that pretty fast, but you have this as a reference. And again, I apologize for any mispronunciation or miscommunication. Thank you for watching, and have a great day.